Hello and welcome. My name is Alex and I'm going to be talking about Fréchet distance on uncertain trajectories. First of all, we should define the concept of an uncertain trajectory. Let us look at an example. Here you see the map of a part of the city of Eindhoven in the Netherlands. In particular, you can see the railroad going in the northwestern direction that goes to another city. The city is close by, so you can also cycle there. Indeed, you can now see GPS data from Google location history. In purple you see the train journey and in blue you see the bike trip. Suppose we want to know how similar the two trajectories are. The standard way to check is to construct polygonal curves on the data and use some distance metric, such as dynamic time warping or Fréchet distance. However, the blue curve has some weird artifacts that will affect our similarity measure. In addition to the measurement location, collected data includes accuracy estimate, represented as a disk of a certain radius. It is feasible that at the time of measurement the object really was anywhere inside the disk. If we take this information into account, now the simple straight line trajectory is feasible. We can see that it will give a very different result than the polygonal curve on the measurement points. So, it is important to take uncertainty into account. If we now abstract away from the precise trajectories, and then abstract away from the map, leaving only sequences of disks, we get uncertain trajectories. They consist of uncertain points. Each uncertain point in our case is some region, and the true location of the object at measurement time lies somewhere in that region. We are thus interested in similarity of two such uncertain trajectories. We focus here on measurement uncertainty and we connect measurements with line segments. We distinguish two uncertainty models, indecisive points where the region is a discrete set of points, and imprecise points where the region is some convex region, such as a disk or a line segment. A sequence of such regions is an indecisive or an imprecise curve, or trajectory, we use the terms interchangeably. If we pick a point from each uncertainty region, we get what we call a realization of an uncertain trajectory. Now that we have defined the uncertainty model, let's have a brief refresher on the similarity measure we use. We use Fréchet distance and discrete Fréchet distance. We focus on the discrete version in our examples in this talk. You can think of it as Fréchet distance restricted to vertices or as dynamic time warping, where you replace summation with taking the maximum. Let us have a look at an example. We consider different matchings or couplings of the vertices of the two curves. We have to match the first points of the curves, then we can jump to the next vertex on the first curve, on the second curve, or on both. We can never go back along the curve. In this example, we start by matching the first points, then go forward on both curves, then only go forward on the first, then again on both, and finally only on the second, so the last points are matched up. The distance for this matching is the bottleneck distance determined by the pair that is furthest away. The discrete Fréchet distance is then such bottleneck distance for the best possible matching. Continuous Fréchet distance is similar but considers the matchings over the entire curves and not just the vertices. With that in mind, we should define what we are looking at here. In these examples we have black and blue trajectories. The points that are close together are possible locations for a single indecisive point. We can go over all the possible realizations of the two trajectories and find the one that gives us the lowest or the highest Fréchet distance. For example, these realizations give us the lowest Fréchet distance, which we call a lower bound. The red line shows the bottleneck in the optimal matching. And these realizations give us the upper bound distance, so the largest possible distance. Finally, if we assume some probability distribution for each uncertainty region, we can talk about expected distance. Here we assume that each location is equally likely, so we assume a uniform distribution for each uncertainty region independently. The expected distance then simply averages the distance over all the realizations. In the imprecise model, we have to take an integral to find it. Now that we know the problem we are solving, let us discuss the results we have obtained so far. First of all, Anne and others have already presented a polynomial-time algorithm for the lower bound discrete Fréchet distance. It is shown for the disks case, but it is straightforward to extend this to line segments and indecisive points. There is also joint work of the authors of this abstract with Zhenglin Fan and Benjamin Reichel covering the lower bound continuous Fréchet distance, showing somewhat surprisingly the distinction between the different models. In this talk, we will be covering the rest of this table, showing the hardness results for upper bound and expected case for both discrete and continuous Fréchet distance. In particular, we find that the decision problem for upper bound distance is NP complete in all the models we consider, and we find that finding expected distance is number p hard in some settings. As a footnote, the class numP is the counting counterpart of NP. For instance, number sat, the problem of counting the satisfying assignments to a Boolean formula, is number p complete. So, many problems turn out to be hard. We somewhat alleviated for indecisive trajectories by showing polynomial-time algorithms for a restricted version of the problem using time bands, a concept we shall explain later. With that being said, let's dive in and see how these proofs work. We will show the construction and explain how it leads to the proof for one of the settings. We consider the indecisive points model and look at the upper bound discrete Fréchet distance. We give a reduction from satisfiability problem. We construct two curves, a precise one, capturing the formula structure, and an indecisive one that has an indecisive point for every variable. Each indecisive point has two locations corresponding to true and false as shown on the right. Consider a specific clause of a formula and a certain variable x. For this combination we choose one of the 3 points on the precise curve in blue, so that if we then choose a satisfying assignment for this clause, we get a large distance. So if the clause has a literal x, we choose the bottom point, so if we assign x to true, the distance is above 1, and otherwise it is below 1. We position the point symmetrically for the literal not x. If x does not occur in the clause, we place the point in the middle at 0, 0, so whichever assignment we choose, the distance is below 1. We do this for every variable given a clause. To ensure that we match up the right points, we introduce synchronization points. The positioning makes sure we either get the distance of 1 or 1 plus epsilon, depending on whether the clause is satisfied. Finally, we introduce synchronization points at the beginning of both curves, so the start of both curves is matched up. The need for this will become clear later. Let us explain this a bit more with an example. Here you see the entire construction. We consider a given clause and an assignment of variables corresponding to a specific realization of the green curve. Starting with x1, we can see we get the large distance since setting x1 to true makes the clause satisfied. With x2, the distance is small, as setting it to false does not affect the clause. Finally, x3 should be irrelevant no matter which value we assign to it, and indeed the distance is small. So we get the large distance here because of our assignment to x1. On a side note, note that all the blue points are close to the origin. Consider this construction at a higher level. We construct a precise curve by combining curves for all the clauses, and an indecisive curve by prepending and appending the origin. Suppose that, for instance, C4 is not satisfied with some variable assignment, then the matching with the variable curve will yield the distance of 1. We can match all the other clauses to the origin and get the overall distance of 1. Due to the synchronization points, this is optimal. So the formula is not satisfied and we get the distance of 1. Now suppose that all clauses are satisfied. Then any of them yields the distance of 1 plus epsilon when matched to the variable curve. So no matter which clause we choose, the best matching we can get will yield the distance 1 plus epsilon. So the formula is satisfied and the distance is 1 plus epsilon. As we are looking at the upper bound, we are trying to find the latter case. So if a satisfying assignment exists, then some realization yields a large distance, and so the upper bound distance is large, otherwise it is small. so we conclude that the problem is NP-hard. This concludes the proof sketch for the highlighted case. The extension to the disks and line segments follows by simply replacing the uncertainty regions appropriately in our construction. The extension to Fréchet distance is straightforward and yields different distances. The expected case for the indecisive points is simple since every realization corresponds to a single variable assignment, and so counting how many times we get a large distance corresponds to counting the number of satisfying assignments. This gets more difficult for imprecise points. We managed to come up with an extension that allows us to tackle the line segment case for the discrete Fréchet distance, but the other cases get mathematically complicated quickly in our construction, although we believe they should be hard too. We have seen that the problems we consider are hard in many settings. We shall now introduce the concept of time bands to alleviate the issue in some restricted scenarios. The standard algorithm computing the discrete Fréchet distance uses dynamic programming on the prefixes of the trajectories. If we consider the decision problem, then we simply fill out Boolean values in the table. In this example, the highlighted cell corresponds to matching the third point on one curve to the second point on the other curve, and any monotone path from the bottom left cell corresponds to traversing a valid matching up to the current point. If we consider all the couplings, we find that the number is quite high. This is prohibitively expensive in the upper bound problem. So we aim to reduce the number of options we need to consider by introducing time bands. The example shows the time band of width 1, so the ith point on one curve can only be matched to the ith point on the other curve, or the one before, or the one after. Similarly, the grayed out cells in the table are now not considered. Using this concept makes sense in the scenarios where trajectories are regularly sampled or represent some form of interaction between objects, so where we want to enforce similarity in time and the point indices act as proxy for timestamps. We do not have the time to go into details, so we just describe the results. All of them are done by a somewhat technical but reasonably straightforward dynamic programming approach. We fix some constant width w of the time band and consider indecisive trajectories of n points with L options per point. In the simplest case, where one trajectory is precise, we get the running time polynomial in L and n but exponential in w for the upper bound discrete Fréchet distance. If both trajectories are indecisive, the dependency on L to the power of 2w is less nice, but it is still fine for small l and w. We can extend the result to the expected value computation. Finally, we can also obtain polynomial-time algorithms for continuous Fréchet distance. This involves more technicalities, but the algorithms still run in time polynomial in n. So we have covered the plethora of hardness results for the upper bound and expected case in different models for both discrete and continuous Fréchet distance. For indecisive trajectories, we discussed polynomial-time algorithms for constant width bands for all the applicable cases. This concludes the talk. Please contact me if you have any questions, and thank you for listening.